Section 14.6, the pH scale. Personnel working in food processing, medicine, agriculture, spa and pool maintenance, soap manufacturing, winemaking measure the concentration of acids and bases of solutions. Although we have expressed the hydronium and hydroxide as molar concentration, it's more convenient to describe the acidity of a solution using the pH scale. On this scale, a number between 0 and 14 represents the hydronium concentration for common solutions. A neutral solution has a pH of 7 at 25 Celsius, an acidic solution has a pH less than 7, and a basic solution has a pH greater than 7. When we relate acidity and pH, we are using an inverse relationship, which is one component increases while the other decreases. When an acid is added to pure water, the hydronium acidity increases. When a base is added to pure water, it becomes more basic, which means its acidity decreases and the pH increases. In the laboratory, a pH meter is commonly used to determine the pH of a solution. There are also various indicators in pH papers that turn specific colors when placed in solutions of different pH values. The pH is found by comparing the color on the test paper to the color of the solution to a color chart. Figure 14.5. On the pH scale, values below 7 are acidic, a value of 7 is neutral, and values above 7 are basic. One molar hydrochloric acid has a pH of 0. It's extremely acidic. Gastric juice, or your stomach acid, is 1.6. Lemon juice, 2.2. Vinegar, 2.8. Soft drinks, carbonated beverage, 3.0. Oranges, 3.5. Apples, 3.8. Tomatoes, 4.2. Coffee, 5.0. Bread, 5.5. Potatoes, 5.8. Urine, 6.0. Milk, 6.4. Water, 7.0. Drinking water, 7.2. Blood, 7.4. Bile salts, 8.0. Detergents, 8 to 9. Seawater, 8.5. Milk of magnesia, 10.5. Ammonia, 11. Bleach, 12. And 1 molar sodium hydroxide solution, which is lye, Drano, is 14. Calculating the pH of solutions. The pH scale is a logarithmic scale that corresponds to the hydrogen ion concentrations of aqueous solutions. Mathematically, pH is the negative logarithm in base 10 of the concentration of hydronium ions. So the pH is the negative log, or the negative logarithm, of the concentration of hydronium ions. Essentially, the negative powers of 10 in the molar concentrations are converted to positive numbers. For example, a lemon juice solution with a hydronium concentration of 1.0 times 10 to the negative 2 molar has a pH of 2. This can be calculated using the pH equation. The negative log of 1.0 times 10 to the negative 2 is 2. It's the negative exponent of the concentration. The number of decimal places in the pH value is the same as the number of significant figures in the concentration of hydronium. The number to the left of the decimal point in the pH is the power of 10. So if it's 1.0 times 10 to the negative 2, there's two significant figures, so there must be two zeros after the negative 2 becomes positive 2. Because a pH is a log scale, a change in 1 pH unit corresponds to 10 times change in the amount of hydronium. It's important to note that the pH decreases as the hydronium ion concentration increases. For example, a solution with a pH of 2 has a concentration of hydronium 10 times greater than a solution with a pH of 3 and 100 times greater than a solution with a pH of 4. pH calculation. The pH solution is calculated from the concentration of hydronium using the log key and the changing sign as shown in problem 14.7. When we need to calculate the pH from the hydroxide, we use the W sub K to calculate the hydronium concentration, place it in the pH equation, and calculate the pH of the equation as shown in practice problem 14.8. POH. The POH scale is similar to the pH scale, except that the POH scale is associated with the concentration of hydroxide ion of an aqueous solution. The POH is the negative log of the concentration of hydroxide. Solutions with high OH concentrations have low POH values. Solutions with low concentrations have high pH values, POH values. In any aqueous solution, the sum of pH and POH is equal to 14, which is the negative logarithm of K sub W. The pH plus the POH is always 14. For example, if the pH of a solution is 3.5, the POH can be calculated as 14 minus 3.5, which is 10.5. A comparison of concentration of hydronium and hydroxide and their corresponding pH and POH values is given in Table 14.8. Table 14.8, a comparison of hydroxide concentration, hydronium concentration, and the corresponding pH values at 25 Celsius. 10 to the 0 has a pH of 0, and 0 plus 14 is 14, so the POH is 14. 10 to the 1 has a pH of 1, and so its POH would be 14 minus 1, which is 13, all the way down. Calculating the concentration of hydronium from pH. If we're given the pH of a solution and asked to determine the concentration of hydronium, we need to reverse the calculation of pH. The hydronium concentration is 10 to the negative pH. For example, if the pH of the solution is 3, we can substitute it into this equation. The number of significant figures in the hydronium is equal to the number of decimal places in the pH value. Hydronium ion concentration is 10 to the negative pH. 10 is negative 3.0 equals 1.10 to the negative 3 molar. For pH values that are not whole numbers, the calculation requires the use of the 10 to the x key, which is usually a second function key. On some calculators, this operation is done using the inverse key and the log key shown in problem 14.9.